continue our discussion of root finding methods. So just in summary of bracketing methods, we had basically for bracketing methods, I have to first find the bracket. That means that I have to find a segment on which function is positive on one end, negative on the other end. That gives me a bracket to start with. And I will often have to do that graphically. I will have to plot the function and investigate it a little, or keep plugging in values until I stumble upon a good value. So it can be difficult if I just continue zooming in graphically. It might be difficult to find an accurate answer, so we need something better than that. And there's two methods that we've talked about in this category. Bisection is a simple one. It's straightforward. I just keep holding the interval and picking the subinterval that is also a bracket. And in false position, you actually look at the magnitude of f of x and try to replace it with something that converges faster. Whether it actually converges faster or not depends on the function, and you often cannot know that beforehand. There are some things that we have to, and we actually hit that problem last time. So I sent an email about it, but we use this code from bisection and in false position, and it was working just fine in bisection. And that code, initial code I posted, didn't have this part. Okay? So basically I had two strict less than 0 and fx2 times fxr less than 0. And in case that you actually really hit that fxr is 0, it's not going to update your next xu and xl properly. And that caused an infinite loop in false position method that I was trying to fix last time. So in false, it didn't actually cause problems in bisection. So this is a bug that actually showed up later. So basically two things that are good to put in. It's always actually, for one reason or another, it's good to limit your number of iterations. Okay? So just set up an iteration counter and stop at 1,000 so you can actually go and fix the problem without it constantly running. That's one thing. And basically here is the actually problem where if I execute this, so basically this is the case where fxr is equal to 0, and we actually hit this case in false position. So if I actually run this, it works really fast. So basically in 4 iterations I will find, so this is the plot of my relative error, okay? And I find a solution in 4 steps. And at that 4 steps, if I actually evaluate fxr, it's a 0. So my loop didn't stop last time around and didn't update things correctly. So if you hit fxr is equal to 0, then what you should do, you should set both xu and xl to be that value of fxr, and you're done. Okay? So that will actually stop the loop. So that is the correction of things from last time. And if I actually, so I am actually computing relative error. So for each, I will actually both take xr and all version of xr, which I kind of remember. I'll put in the code. So basically when you have iterations where you don't know the true value, then the way you approximate the error, or relative error in this case, is you take the current, your value, your current estimate, your previous estimate, their difference, and divide by the current estimate. So this is, instead of your true value, you use xr. Okay? So if I actually run bisection in this case, it's going to be running, oh yeah, so it's going to be running 11 steps, so it takes a little longer. So this is the case where false position works rather well. That doesn't mean that it always does, so just, it's kind of like a case-by-case basis. So that summarizes bracketing methods. Here's actually an example where false position will take forever. This is function x to the 10 minus 1. A good bracket is 0, where I have -1, and for instance, 2, where I will have something really large. And because of that very big difference, if you actually try to see your next XR value will be here, right? So that's your first approximation of the slope, but it's obviously a very bad approximation of the slope in this particular case. Okay? So because of that, this is going to be next value. So this is going to actually go very slowly towards this value where it's actually 0. And in this case, halving the interval would be much faster. Okay? So again, it depends on the function. So functions essentially, the functions that will work well, we will hear this sound every time I get an email. Watch for it now. So basically the functions where false position works well are those where where this difference like this, which is a approximation to the slope, really approximates the slope well at the point at where my function is actually 0. And in this case, that's very far away from actual derivative of the function. Okay. So next thing, we're gonna really. Why can't it stop? Let me just a moment. Okay. Okay. So next thing, we would like to explore the methods where I can actually just start with some initial value, whatever it is, typically 0, because that's the first number I can always think of. Okay. And then can I just iterate and find a solution? That would be nice, wouldn't it? Instead of finding this bracket and using the graphical methods to find the bracket. Well, there's no perfect solution to this situation, but we will outline a number of methods. Some of them are faster than the others, but they don't always work. So one of the key messages in root finding is nothing ever always works. You have to kind of look at things case by case. So the way we often design numerical methods is we kind of look at our problem and try to rearrange things and see whether I could figure out some way to iterate towards a solution. So if I have a function that is x squared plus x minus 1 is equal to 0, okay? Then I can actually look at it and say, okay, I can rearrange this so that x is equal to minus x squared plus 1. Okay? And that actually suggests a way to iterate. Okay? I can guess some values of x0, okay? And my next iteration, x1 for instance, so x1 will be minus x0 squared plus 1. Okay? Then x2 will be minus x1 squared plus 1. And I will keep going. In general, I form this as a x is equal to, I'm going to call this right-hand side g of x. And the way I iterate is like I guess one starting value, and then at every step I'm going to say, well, my next value, xk plus 1, is g of xk. And then xk plus 2 is g of xk plus 1. And I know how to evaluate g, so this shouldn't be difficult. This is a very simple loop that I can simply form. Right? Well, great. So now that's a sweet idea. Does it actually work? And when does it work? So obviously there's multiple ways I can rearrange this equation. So for instance, if I had only sine x is equal to 0, okay, I can just add x to both sides and create myself this situation x is equal to g of x. Right? So basically I start from the equation I have and I kind of transform it algebraically into something that looks like x is equal to some function of x. Okay? And that suggests iteration. Now, just because I was smart pants and I did that doesn't mean it's going to work. So let's analyze situation where it's going to work. So what I'm actually switching from, I'm switching from finding a root of this function, f of x, to something that is basically an intersection of function x, right? That's on this side, and function g of x that is on the other side. So I'm looking for the intersection. And that's actually slightly conceptually easier. So what are the parts where this is actually going to work. Okay? Turns out that it works only in some region where I'm at, where I'm searching for 0, typically around my starting point. My absolute value of g prime of x is less than 1. Let's see why is that. So let's force on this, let's figure out this first case. So in this first case, I'm going to point, okay? This is my function x. So I have x is equal to g of x. This is my function x, okay? And this is my g of x. And let's say that in this case, the slope to g of x is relatively small. It's positive and small, and let's say that it's less than 1. What will happen then? Okay? Well, what will happen is I will start from some value x0. Okay? So my first x1 is g of x0. So that's right here. This is g of x. So this is g of x0. Right? Now, where is my x1? So that's my x1 actually here. But if I walk myself over to the graph where both x and y values are the same, that's my function y is equal to x, then my x1 is here, but my x1 is right here as well, right? Because this is a function where y and x are the same. So this is my x1. So then I look at where is my g of x1. It's right here, because this is graph of g of x. Okay? And then I go and walk myself over and look at the cross section with this y is equal to x. It's right here. So this has value of y, which is equal to x1, x2, okay, as well as value of x that is equal to x2. Great. So this is my x2. Okay. So then again, I'm going to look at g of x2, which is my x3. Okay. So I'm going to walk myself over to this graph over here. So this is my x3. So I can look up my x3 right here. And I can actually see how x1, x0, x1, x2, and so forth, they're really kind of sliding down to this point that I'm actually looking for, which is intersection of these two graphs. So this is explaining geometrically where these points are. I'm literally looking for these points on these two graphs. And I can see how succession of points is actually kind of sliding down because of this gentle, you could say gentle slope that g prime, the function g of x has.
Why
Yes?
would you want to use these different types of versions?
To speed up. So bracketing methods are not always the fastest one. And also I have to find the bracket. And I would like to relieve myself from finding a bracket. So I'm now looking for so-called open methods that just start from an x0 and rate. Because that's easier. I just throw in the number and I keep going.
So are these faster for different circumstances?
So this is actually, in this case, sometimes it's going to be faster, sometimes it's not going to be faster, but here I don't have to, if I have a function g that works, I don't have to look for the bracket. So I don't have to look for where's my function less than 0, where's my function larger than 0 to get myself. So it's just different options, having options. And it depends on the function what will work the fastest. So okay, great. So I will kind of in this case just slide down. Now let's look at the different case. Okay, let's look at the case where I actually have not so gentle slope. So this slope is much larger than 1 of g of x, right here, this one. So basically then what happens is I start from an x0 and I actually want to get here, right? This is what I want to find. x0, so this is my g of x0, so that's my x1. Then I walk over to this graph y is equal to x. It's right here. This point has both x and y value the same, and it's equal to x1. Okay, so this is x1. Then g of x1 is right here, and that's my x2. Okay, so then I walk over to this graph. This is my value x2, both in x and y. So this is my x2. So I'm starting to actually walk away from my point because of the slope of the graph that is large. Okay? So in this case, we say that this iteration will diverge. It will not find the
root here.
So in general, and you could do the similar for negative values. So as long as your G prime is a gentle slope that is an absolute value of less than 1, okay, then the method will converge. It might oscillate slightly if it's negative, but it will still actually go around the point and eventually get there. And it will diverge if G prime of x is large in absolute value. All right. So as an exercise, can you, for instance, this example B, can you come up with 2 or 3 different ways to this fixed point of iteration? So everybody jot down something, and let's see if, as a class, we actually come up with different versions. So take a minute. So basically transform, I'm solving a problem, x to the 4 minus x minus 10 is equal to 0. And I'm asking if we can find 2 or 3 different ways. Some of you will find one way, the others will find the other. Let's see how creative we are. And if you want, take a look at the convergence. So just because you can come up with x is equal to g of x, that doesn't mean it's going to converge. So thank you for the suggestion. Let's look at the convergence as well. Yes?
So obviously, one would be
Yeah, so one would obviously be x equals to x to the 4 plus 10. Now let's say that I'm looking in the area where x is equal to 2. I don't know. In that area, what is g prime of x? So one version would be x is equal to x to the 4 plus 10, right? So g prime is this. G of x is this, right? So what is g prime of x? So 4x cubed. Is that always small? Okay. So if I'm, for instance, if I start from x is equal to 2, this will diverge, right? Because g prime is really big, so no matter what.
How does it diverge?
So it will just spiral away from the root instead of going towards the root.
What's the condition for it to converge?
Absolute value of g prime of x should be less than 0. So absolute value less than 1, I'm sorry. So actually, I could actually look at x's where this is true, right? So I could actually I can find the limit on x's where which is true, and I do hope that those x's are close to the 0 that I'm looking for, and if they're not necessarily going to happen. Okay. What is another option I could have? How could I rearrange this? Yeah, so x to the 4 is equal to x plus 10, which means that x is basically x plus 10 to the 1/4. Okay? Whoops. 1 over money. So when I look at the g prime for this, okay, it's 1/4 x 10 to the minus 3 over 4. And that has actually a better chance of being less than 1. Okay? So this second function has a better chance of convergence. Okay? And the way to test it, of course, you can always just test it. The way to test it is just to set up an iteration where you just keep updating your x, okay, based on this. So your next x, xk plus 1, is your old value of x, this function of it, okay? And you just start from some value. See whether. Okay, yes.
So you say that you can
set up an iteration to test x values as you go on and see what it will do.
Yeah. You can just try out a couple of starting values.
Is there another way to do it? Another arrangement that I'm not seeing?
Oh, I don't know. Well, you can always add. No, I don't know. You could now get creative. I mean, square of something, or I could look at. I don't know. You could, but I don't think that it's necessarily beneficial because I think the second one would work. I mean, any transformation of this works too, right? So just because I have an equation, I can take a log of it or exponential of it or something, and that's still valid. So you can find a way to transform.
What about the factors? Like, you somehow found the factors could be used like one part of that equation. Is that equal to 0?
Yeah, so the one good point here is actually, this is x to the 4 minus x minus 10, so I potentially have 4 different roots. Okay? And all of these numerical methods, they will find one of them. Okay? So once you find one, you factor it out and you keep looking. You divide the function by x minus that root. And then you keep looking. Yes?
Second fixed point iteration like the g prime of x, is that the second derivative of your b?
It's derivative of this, right? So it's 1/4
Oh, okay.
x plus 10 to the minus 3 over 4. Right? And that has a much better chance of being small. Okay? Okay. The most popular method is so-called Newton's method, okay, or Newton-Raphson. Okay? This basically says, if I look at a graph of my function, and let's say that I have 2 close iterations, okay? Basically, so if I'm at this point, I want to kind of slide down this route using the slope of the function, so basically approximation to the function slope here. And that slope, approximate of it, is of course given by this difference here, this divided by this. Let's see what this is. So this is f of x1 minus 0, and this is xi minus xi plus 1. So that is approximately the slope. And I can actually then look for xi, what should, according to this equation, what should xi plus 1 be? So when I just set that as equal, I will actually find xi plus 1, and that you can verify for yourself that this is the formula that you get when you find out xi plus 1 from this arrangement here. So basically, there's an iteration suggested here that my next xi plus 1, based on some previous guess, is xi minus f of xi divided by f prime of xi. Okay? This method, if it works, when you find a good starting point, it's fastest of them all. It kind of, there's something called quadratic convergence, so-called quadratic convergence. So that means that error slides down as a quadratic function as opposed to linear. So essentially, it's very fast when it works, but it doesn't always work. So again, we have trial and error. And we can also derive this method from a Taylor series just by dropping all of the second derivative and higher terms. So there are some pitfalls here. Okay? So here are some cases where this function is not going to work. So there's A, B, C, D. Let's look through them. So for instance here, if I start at x0 is here, so I basically what I call slide down my slope. So I find the slope at this function, and this is where my x1 would be. Okay? Then my next step, and watch out, I might ask you on the test also to find the solution graphically. And in this case, you just at the first point you have, you draw a slope right here at this point and see where it intersects this 0 here. And that's your x1. And then you repeat the process. So again, I draw the slope. Okay? So my x2 is here. Then if I go again, this next slope will send me, woo, somewhere here outside of the range, okay? So I'm gonna kind of keep getting oscillating and get further and further away from actually the point where I'm looking for. I'm looking for a 0 here. So this happens because I have inflection here, okay? And that causes the problem. So basically near where I have f double prime of x is close to 0, is equal to 0, that's an inflection point that causes my oscillation and kind of ultimately diverging from a solution. Okay. Another problem I have if so this is partly quadratic right here. So I have sort of like a minimum, okay? And I might actually go oscillating around here. So let's say that I start from x0, okay? I draw the slope. My next point is here. Where's that slope? X1 is right here. Okay, so this is the slope I'm sliding down to. Okay, so this is my x1. Then I go here, and then my slope takes me to x2. And then next slope takes me to x3. And then x2, x4. So what I'm actually looking, I end up finding the minimum here, where f prime of x is 0, okay, instead of f of x being 0. So I'm not going to necessarily find what I'm looking for. Okay? And then if I have a near 0 slope, so something that is nearly parallel to this, so that was actually the case here as well. So any kind of near 0 slope, like if I really hit it right here, okay, then it's extremely, I don't even know how is this slope to that, but okay. Error in this textbook. Then basically you will start like flattening and getting away. So if you actually have close to 0 slope, this f prime, or 0 slope itself, so this is precisely where I have a 0 slope, this is a disaster because you're going to be sent to infinity. In general, there is no criterion I can check. So it's a trial and error, and it depends on the nature of a function. And the best remedy is actually to guess sufficiently close to root, or have multiple guesses that you try for that are separately. So for some functions are simply difficult, but we still have to deal with them on a regular basis. All right. Now, this Newton formula, it actually works when I have a function that I can compute f prime of. Okay? If my function is theta, okay, then I actually have to find a numerical way to compute f prime, okay, because I don't have a formula that I can do a derivative of. And in that case, we modify this Newton method to I'm just going to approximate f prime with f of xi minus 1 minus f of xi divided by xi minus 1 minus xi. So it's a simple approximation with the slope. So imagine if this was divided by, and then if I figure it out, this is what I get. So basically I'm just substituting a simple approximation for f prime into this formula, and this is so-called secant method. So this is 4 cases where it's not easy to compute f prime for whatever reason. Okay. Now, in review, so I have bracketing methods, which is what we covered and finished last time, and these open methods. I could have fixed point iteration where I reformulate my problem as xk plus 1 is equal to g of xk, or Newton-Raphson method, xi plus 1 is equal to xi minus f of xi divided by f prime of xi, and secant method. Okay? Secant method simply replaces this with an approximation, so this is my third version. And in open methods, I start from one guess and I keep computing. Now I have here tried to solve Peng-Robinson root finding with both fixed point and Newton-Raphson methods. I'll actually let you pick which problem you want to solve. If you want to work on the ones we worked so far, or if you want to work on this problem. Okay? Either way, give it a try. Okay? So try to solve one of the problems we worked with, maybe one of these. If you want to go with, maybe you want to try one of these, okay? I'm gonna leave it to you. But what I want you to do is I want you to compare fixed point method and Newton's method. Okay. So let's get going. So this method and this method for one of the problems we worked on. This one is kind of challenging for fixed point. So if you want a good challenge,
Which one's easiest? First one?
well, I think the easiest one to program is the one x to the 4 minus 6 minus
Can I
10.
do that one?
This kind of just ugly to type in.
Can I do that one? That actually.
If you want to. The point is to give it a try, okay? Both methods give it a try. So your option is one of these or this one. Here's your fourth option. Take a pick. I'm pretty much sure like 99% of the class will listen. There'll be one person. It's again, it's just conceptually, give it a try. Yes. So whatever function I have, and this function, I want to rearrange it so that I have x on one side and something else on the other, and there's something else I'm calling g.
Okay.
So a simple one would be x is equal to x to the 4 minus 10. But we show because x to the 4, it might actually have issues converging, unless you're really careful, because your g prime of x has to be less than 1.
How do you set find 0?
Do you use 0? The original.
So if this is true, right? If this is true, then x is equal to x to the 4 minus 10 is the, right? So that's true as well. So that motivates an iterative version where I start with something and I hope that I'm going to get closer. It doesn't always work, but it just motivates what to try.
So we just initialize x at some point. Doesn't matter
And
what.
then you march. Okay. And then another version would just put x to the 4 is equal to x plus 10. So x is 4th root of x plus 10. And that has a much better chance of converging. I'm gonna stop the video because I'm gonna now keep walking around.